Hello, in this video I'm going to look at a exam review for Math 1324, Season 1. So in the first two chapters that we worked on, you looked at properties of functions, you looked at domain and range, you looked at exponential functions and logarithmic equations, and even quadratic functions and rational functions, actually. But we also looked at, some simple interest and compound interest, continuous interest, and then also some annuities, which dealt with periodic payments that in any case was for saving up for a large purchase, or setting up some kind of fund that you'd like to, have at the end of the period. So let's think about this in general, just for the sake of coming up with some formulas, for example. Now, you talked about domain and range. So in either case, if you're talking about domain and range, then we know that if we have an equation that's graphed in the x and y plane, and, it doesn't have to be any particular function, but let's just say that we have this. Then in any case, we can say that, for example, that the domain of this equation, the domain of this one is going to be from minus infinity to infinity. Okay, but we can also talk about the range, but, in either case, if we wanted to talk about the range, then we would know that it would go from negative infinity up to whatever the highest point happens to be. In any case, if we had that was 4, then, yeah, we would say that that's going to be the range is from bottom to top, so we would say minus infinity to 4 in either case. Actually, it should be a bracket, right? Okay. But we also looked at how we can actually evaluate functions, for example. Like if I have that a function g of x is defined as negative x squared plus 2x plus 6. If I plug in 2, then in that case that means negative 2 squared plus 2 times 2 plus 6, which this is going to be minus 4 plus 4, and that's going to be plus 6, which in actuality, what happens? You have that the minus 4's cancel out, and it leaves you with just positive 6. Okay, so that would be, how we evaluate that function. But what if I wanted to know, for example, what the graph looked like, or what if I wanted to know what the x-intercepts are, y-intercepts, and so on? Then in that case, that would mean that I would have to complete the square. I would have to take g of x equals to minus x squared plus 2x plus 6. I would then take out a negative, so I have x squared minus 2x plus, we take half of the middle term, which in this case, half of the middle term is negative 1, and we square it, so we get 1. But we'll also go ahead and take the 6, and we're not going to subtract 1, but we're also going to add 1. So what does that do? It rewrites it as x minus 1 to the second power. 6 plus 1, that's 7, is it not? So we have that's going to give us that equation. Now, note that, for example, that if I wanted to find the x-intercepts, what would I need to do? Well, I would need to set it to 0, where we have 0 equals to minus x minus 1 squared plus 7. But then what do? You set it to 0, right? So by setting it to 0, you end up with the following statement. You end up with that x minus 1 squared equals to 7. How do you solve that? Well, you take the square root, right? You take the square root, and you get that the solution would be that x equals to 1 plus or minus root 7. Now, of course, those are rational numbers, but not a big deal actually, because I know now a lot of information just about that one graph alone. What do I know? Well, I happen to know that, for example, that the function as it's written has negative x minus 1 to the second power plus, what did we say, 7, right? Well, if I was to graph this in the x and y plane, then I would have that this would be a parabola, but it would be upside down, where we would have that the maximum would be at the vertex. What is the vertex? The vertex is the point that gives this a 0, so that's going to be 1, and then the constant 7, so 1 comma 7. And what do we classify this as? We classify this as a maximum. Now, in either case, though, what if we wanted to just plug this into our calculator or even to Desmos? Then we can actually do that. Why not? So if we do that, let's see. All right, so we want to set up a little graph, right? So we have y equals to, now take in consideration that if I go ahead and I plug it in as originally stated, then in that case, we'll get the same thing. But we'll go ahead and say x minus 1 to the second power, and then plus 7. Okay, so there's the graph right there. And we have that. There's the maximum that we had found. And here we are with the x-intercepts. Negative 1.646 and 3.646. Note that it is as easy as, point and click. Which that's nice. But of course, if you're having to use a TI-8384, then we can do that too. But, I guess I should go back, right? So if I wanted to talk about the domain of this equation, note that it would be from minus infinity to infinity, and that the range would be from minus infinity to 7. So what does that tell me? That tells me that in terms of this function, we're just going to say that the domain is minus infinity to infinity, and that the range is from minus infinity to 7. That should be a bracket, right? Yeah. Now, note that if we wanted to find the graph of this equation by hand, we probably could have plugged in a few points. I just did a lecture on how to graph equations using the plotting method, of which, it doesn't really take much to do it. You just have to plug in as many values as possible, such as like -2, -1, 0, 1, and then just plug those into the equation. Now note that 0, you would get actually the y-intercept, which in this case is just 6. But if you plugged in 1, that's the one where you get the 1, 7, right? 1 comma 7. And this is 0 comma 6, right? But if you plugged in -2 and -1 respectively, then in any case, you would get that at -1, you get that the value that corresponds to it is actually 7. Okay. But then if you plugged in -2, well, the value that you get is actually 6. So when you do that, that's going to give you, actually, let me go back. Let me go back to the graph, because -2. So let me do this. Why don't we do x equals to -2? And what do we get? -2. What about x equals 2, though? Okay. So I was making a mistake in terms of the computation. So going back, like we said, -2. So we get -2 actually. Okay. So we get -2, sorry. So that will be -2. Okay. So in that case, -2. Now, theoretically, what you would do is you would just plug in all of these points until you get a graph that defines the shape of it. And we had an additional point, right? We had 2 comma 6 also. So this would be enough information actually to get the graph by plotting methods. Okay. Now, if I wanted to, think of, well, what if I was interested in finding maximums and things like that? What if I had that my profit revenue was quadratic? Then in that case, that would mean that I could use the quadratic formula. Not quadratic formula, actually, but the vertex formula, right? Now, the vertex formula is how you would find essentially the maximum a lot quicker, so to speak. So we had that our equation was g of x is equal to negative x squared plus 2x plus 6. The vertex formula that gives you the maximum is negative b over 2a. How do you find the value that corresponds to it? You plug it into the equation. Now, in any case, that would mean that would be minus 2 divided by 2 times negative 1, which is actually going to be just 1. Okay, that's easy. So we end up with g of 1 equals to negative 1 squared plus 2 plus 6 equals 7. Done. So we get that it's going to be the ordered pair 1, 7. And the way that we know that it's a maximum is due to the fact that you have a minus sign. So in that case, that means that you have a maximum. Versus if this was a positive sign, then we would have that it would be a minimum. Now, going from here, what I'd like to do is to actually start looking at some practice problems. So I think it's in order of the math finance. So you did talk about some math finance things. So for example, we have that simple interest. Simple interest is defined as taking the accumulated. Okay, so we have that the interest is equal to a principal times R and T, where the R is in annual interest and T is in years. So that means that if you want to find the future value with terms of simple interest, it's going to be P times 1 plus RT. And if you want to basically look at compound interest, well, compound interest is actually going to be a very larger computation respective to the simple interest because it's exponential in that sense. So you have that the future value with compound interest is a principal amount times 1 plus I raised to the n. Now, I is actually going to be the interest divided by a period, and n is going to be the periodic total payments, m times t. Now, if I wanted to locate the principal value, then in that case, I would just take a, and I would just divide it by the compound, 1 plus I to the n. Now, you could use properties of exponents that say 1 plus I raised to the negative n, and that would be the same exact thing. Now, let's suppose that we have where you take $19,000. Okay, so let's say that the principal amount is $19,000. And let's say that the annual interest rate is 7%. Okay, now let me go ahead and just write it as a percentage, so that way there's no confusion. Now, this money is going to sit for nearly 20 years, but we're going to say specifically 19 years. And it's going to be compounded monthly, so in that case, I use 12. Now, how do I do this computation then? To do this computation, you would say that A equals to 19,000 times 1 plus 0.07 divided by 12 raised to the 12 times 19. Okay, so can we do this computation using a normal calculator? I think so. Why not? 0.07 divided by 12. Okay, don't round. Okay, now I need to raise this to 12 times 19. And we're going to push equals. And we're going to multiply this by 19,000. And push enter. Okay. Now, we're going to round it to the nearest cent. So this is approximately equal to 71,562 and 76 cents. Okay, now suppose that you wanted to find the amount that it accrued, like, the interest rate. Not interest rate, but the earned interest. Sorry. So if you want to find the earned interest, then in that case, you would take the amount that was earned, the 71,562 and 76 cents, minus how much was deposited, 19,000. And then that equals to like 52,000, right? 562 and 0.76. So there's your answer in terms of like, okay, well, what if I wanted to know the interest also that was earned? Now, as it relates to compound interest, we might actually be looking at what is called effective rates. Now, if you ever worked in retail or anything like that, or sold, maybe like a car or anything like that, then you're probably more familiar with the term annual percentage yield. So effective rate that we can notate like this is equal to 1 plus r over m raised to the m minus 1. So let's say that we wanted to find the effective rate for $1. So if we wanted to find the effective rate for $1, then in any case, we can say that if it's invested for 1 year, then, well, it's already, this formula is not, yeah. So, okay, so what we'll do is we'll just say take the dollar, and it's already accounted for, by the way, the principal being $1. So from there, what we'll need to do is take 1 plus the interest. Now suppose that it's invested for 1 year at 8.2% compounded semi-annually. Then that's going to be 0.082 divided by 2, and that's going to be raised to however long this will be. Well, that'll be 2 minus 1. Okay. So let's go ahead and do this computation in terms of the annual percentage yield. So 0.0, okay, let's do this again, right? Oops. Okay, there we go. 0.0862 divided by 2. Okay, plus 1, but squared, right? And then minus 1, right? Okay, so minus 1. Semi-annually. Okay, so 0.082 divided by 2. Okay, so plus 1. Okay, but then square that. There we go. Minus 1. Okay, so this is approximately, when we look at the computation, it's approximately 0.08368. But as a percentage, that would be 8.368%. Now notice that this is actually much greater than the 8.2%. And that's actually correct because it's compounded in any case. So if I wanted to find an effective rate, the amount of which that's being invested is actually, in a sense, not really looked at, because what it's looking at is it's looking at the rate of return basically within the 1 year. Because think about it like this. If I know that the earned interest is calculated by taking the principal, where I have this amount raised to the mt minus p, but then if it was $1, then in that case it's 1 times 1 plus r over m. But what if it's for 1 year? Then it's to the m minus 1. So it's the exact same formula actually. when we think about it. So the amount that was invested is actually not really even considered at all in either case. Now, suppose that we had a different problem where we wanted to find the present value. So finding the present value, we said that you take the accumulated times 1 plus I and raise it to the negative n. So let's say that the amount that you have in the future will be 13,756.41 at maybe like 8.4%. Why not? And this is compounded annually, so we'll just use that m equals 1, and we'll use that t equals to 4. Okay, so in this case, I might want to find the principal value of this amount by just saying that we have 13,756 and 41 cents multiplied by 1 plus 0.084 divided by 1 raised to the well, it's raised to the 4, is it not? Yeah. So we can do this computation using our basic calculator. So, well, notice that that's actually 1.084 when you add it, but that you want to raise it to the 4th power. And then you want to multiply it. Oops. Actually, yeah, I got to be careful with that. That should be a minus, actually. Yeah. This should be a minus because of the fact that it's a present value that we're trying to find that needs to be invested. Okay, so it should be smaller, actually. So 1.084 raised to the 4, but negative, and then we click that, and then we take multiplied by the 13,756.41. Okay, so that means that the amount that should be invested now is 9,962 and 95 cents. Okay, so this is the present value. Okay, now keep in mind that as you're going through these equations for compound interest, that these are just single deposits in either case. So we don't need to think of it in terms of like a sequence. Now, if we had something like where we didn't know the time or the interest rate, this means that we would need logarithms. Now, let's say that you have that $3,000 is deposited, but we say that it's going to grow to $6,000. Okay, but what if this is at an interest rate of 7% where it's compounded quarterly, so 4? Now, what this means is that you would have that the $3,000 needs to be multiplied by 1 plus 0.07 raised to the, divided by 4, sorry, raised to the 4t equals to 6,000. Now, notice that if you divide this by 3,000 on both sides, you end up with 1 plus 0.074 raised to the 4t equals to 2. Now, normally I might say, like, let's go ahead and just use the calculator to solve this, which we are going to use the calculator, okay? Nothing wrong with that. But given that we actually, spent some time talking about exponential functions and things like that, then yes, we might actually need to go ahead and work this out. So to do this, we go ahead and we just rewrite this. How do we rewrite this? We rewrite it by taking the natural log on both sides. So we take the natural log, and essentially that gives us that the 4t is going to move over. So the 4t moves over, so you have 4t multiplied by natural log of 1 plus 0.074, and that's going to be equal to natural log of 2. Now note that, the answer is already there, basically. You have that t equals to natural log of 2 divided by 4 times natural log of 1 plus 0.07 divided by 4, and then that's going to be it, right? Okay, so that's my symbolic answer. I won't even bother trying to simplify this part right here. But let's go ahead and say that we want to figure out what this is, right? Okay. So let's do 1 plus 0.074 divided by 4. Let's see. Okay. And we're going to take the natural log of that. Yeah. So we'll take the natural log of this. We're going to multiply that by 4. And we're going to divide that. So that means that we need to reciprocate it. So there. But then multiply that by parentheses 2 natural log, close it, and hit enter. So notice that this is going to be 9.45 years. Okay. But it says that maybe you want to consider that it's quarterly, right? So that means that we would just round up to the next quarter. So in any case, that would be that you would just round it up to 10 years. So we can just say that it's going to be at least 10 years that this amount will be growing to $6,000. Now, if we use the calculator, though, like Desmos, then in that case, that's going to be not too bad because we'll say 3,000 or 6,000, right? 6,000. And then we'll just put that y equals to 3,000. And then what can we do? 1 plus 0.074 divided by 4. And we can actually raise that to the 4x. And now, let's go ahead and set the window. Now, x is going to be the number of years, so 0. And we'll do like 20 maybe. Now the x-axis, you need to be from 0 to at least like 10,000 maybe. So here's our answer, point and click, 9.453. So if we go ahead and we consider that the amount needs to exceed this amount, 9.45, considering that it would be quarterly, then yeah, you would say at least 10 years, basically. So the answer is at least 10 years. Of course, you just have to be careful with like what the question might say, for example, like if it says to round or not. I'm looking for another question that I can do. Okay, now let's actually talk about annuities. So an annuity is basically a sequence of payments that is being made over time. So we have that there are two formulas basically for the annuities. You have that there's the future value of an annuity. So I believe the way that it's written down in the textbook is like R is multiplied by 1 plus I raised to the n minus 1, and this is divided by I, and then this is going to be that, right? Now the way that I normally do it though is that I use future value equals to the payment multiplied by 1 plus I raised to the n minus 1 divided by I. So the only thing that I'm doing differently is I'm using R as payment and FV is the sequence of sum of the series of payments. So you know, like if I wanted to do like an easy example, like for example, like where I said that I was gonna, you know, say that I want to deposit $100 at an interest rate of 5%, and let's say that it was compounded semi-annually, then in that case I can find the sum of the series by just taking 100 multiplied by 1 plus I. Actually, it's not I, is it not? It's 0.05 divided by 2 raised to the, actually I need to choose the time, right? Let's just choose 3. So 6 minus 1 divided by 0.05 divided by 2, and then we'll just try to figure out what that would be using the calculator. So 0.05 divided by 2 plus 1, and then we'll just go ahead and raise that to the 6th power minus 1. Okay, but I need to divide this by parentheses 0.05 divided by 2, close it, and then hit enter, and then multiply this by 100. That's very interesting, actually, that it only came out to 638. 638. Oops. Okay, so it was 638, and how many cents is that? 77. I'd be very interested to see, like, you know, if maybe I did something wrong. But it seems like that's going to be correct because the payments is 100. How many payments are you making? You're making 6 payments. So in that case, that's $600. So that means that the earned interest is actually just $38.77. But we can actually look at a different example. A different example that uses that, the same formula. Because I can look at the cache layout, but I don't really need to. Now, more than likely, you use something that was like built in the calculator, but I'm going to do this where we look at an example. And let's say that R is $800. Let's say that the low R is 0.0612. We'll use the same compound 2, but we'll use that t is equal to 7. And, you know, these are made up, to be honest. Like, yeah, there's nothing special about these numbers. Like, why is it this? Why is it that? So S is equal to 800 multiplied by 1 plus 0.0612 divided by 2 raised to the 14 minus 1 divided by 0.0612 divided by 2. And then what we're going to do, we're going to go ahead and just plug this into the calculator at this point. Interesting enough, you know, like if you take this course like through a business school, more than likely you're using something called Annuity Tables. If you're in insurance, more than likely you might have looked at amortization tables and things like that. Okay. And I'm going to multiply by 2 instead and divide by 0.0612. And I'm going to multiply that by 800. Okay, let me check my solution. Yep, that's correct. Okay, so the solution, or the amount that it accrues to, is $13,724.76. So if I wanted to know the amount of interest, I'm going to have to take the 800 multiplied by 14 and subtract, let's take the absolute value, 13,724 and 76 cents. And that's going to be, yeah, when you do the difference, you should get 2,524 and 76 cents. Okay, so this is our amount that's earned in 7 years. Okay, now consider this. Usually this is something that's done when your company wants to make like a big purchase, like your company needs like a big replacement of a copier or something, or like a new vehicle or something like that. Or maybe you're just saving up for a washer, perhaps. Now, when we talk about this though, like when we talk about future value of an annuity, and I'm going to stay consistent with the formula that you guys are using in class. So that's going to be 1 plus I raised to the n minus 1 divided by I. And notice that if I don't know the payment size, then that means that R equals to basically SI divided by 1 plus I to the n minus 1. That's just algebra though. So similarly, we could probably say, well, what if we didn't know, but we know that, let's say that there's an annual payment being made for 9 years. So t equals to 9, which means that n is equal to 9 actually. And we have that the interest rate is maybe like 6%. Now be careful. If it did say 6% in the problem, then in that case you're converting it, okay? But let's say that this produces a sum of $77,000, okay? Then how are we going to find the amount that it started with? Well, let's do this. Let's take, let's take the 77,000, and we're going to multiply that times, 0.06 divided by 1, because it's annual, divided by, well, really, you could just say 1.06, right? And that's raised to the 9th minus 1. And then this is equal to the R. Now consider this, that, again, R is just the sequence of payments being made over time. So 1.06, what are we going to raise that to the 9? And minus 1. And reciprocate that, multiplied by 0.06. And multiply that by 77,000. That's right. Okay, so that's going to be, okay, so what did we find? It's going to be $6,700.71. And then that's it. Okay. Now we could probably find the amount that was earned, for example, but we really don't have to actually. Now, of course, if you were trying to set up a college fund for your child or something, or maybe like an IRA account, then it would still be an annuity. But if it was something where you were, let's say, trying to set up an account where you contribute to it, but then you want to live off of it once you reach a certain age, and let's say that you give yourself like 10, 20 years to live off of it, that's not a future value of an annuity, because then it's like you're paying yourself back, sort of like making withdrawals. Because the thing about future value and annuity is it starts from 0. The other thing, though, is that if it's the other way around, where you're paying yourself back, then it should be, or you're paying someone back, then the balance should tend to 0 instead. Different scenarios. Now, what I can probably do, though, is just before I move on, is kind of give you an idea of like how these work, actually. So normally in class, like I might say that I deposited, let's say, I didn't really like that question. Let's say I deposit $250 for 5 years, and it's going to be annually, and the interest rate is going to be maybe like just 3%, you know, so maybe like 0.03. Now look at it like this, the cash layout, right? The cash layout says that you start at 0 and that you end at the 5th year. So we have the 1st year, the 2nd year, the 3rd year, and the 4th year. Now, I know that I'm making these deposits on an annual basis. So we have 250, 250, 250, 250, and 250. But the question becomes, how much is earned after each deposit? Well, to do that, you use the formula, the present value times 1 plus I raised to the n. Now, in that case, that means that in actuality, that means that basically you're going to have the 250 is by itself, because when it's first deposited, nothing's earned. So that means that on the first year, you have $250 plus how much is the second year? It's going to be the 250 originally started, but then with the compound interest taken into account, which is 0.03 raised to the, I'm sorry, I think it's raised to the 1, yeah. So plus 250 for the second year, 1.03 to the second, plus 250, 1.03 to the third. But then we need our final year, right? Let me just move this over. We need our final year, which our final year is the 250 times 1.03 raised to the 4th power. Okay, now note that this computation, this computation can be intimidating. Another case, let me see. So if you do the computation, and unfortunately, maybe I can use a calculator. So let's go ahead and just use the calculator where we have that we're going to plug this in. Well, we know that it's basically 250 all the way to 250 multiplied by 1.03 plus 250 multiplied by 1.03. Now it's going to be squared plus 250 multiplied by 1.03 raised to the 4th power. No, 3rd power. Okay, gotta be careful with that. And as you can see, it doesn't even fit in the window. So imagine if you had an annuity that exceeded, I don't know, like 10 years at least, then yeah, we would be typing this in for a while, right? But something like this can be done in Excel, probably, I imagine. Ooh, that's not good. I need to put the 3 and then raise it to the 4th power. Okay, so let's push enter and see how much money we got. 13,000, or no, 1,327 and 28 cents. And that's if I did it correctly. Okay, so let's see. How do we do this? We do, okay, how about this? Alpha y equals, and what do we need to do? It's 1.03. It has to be raised to the power. So it was done for 5 years. So now it's raised to the 5th power. Okay. Put -1 and just divide by 0.03, right? Okay. Let's see what that ends. Okay. Times 250. There we go. So we got the same thing. 1327. $13.27. And how many cents is that? Oops. 28 cents. Okay, so 28 cents. Okay, so we have that this is the annuity in either case. If I wanted to find the earned interest, basically it would be kind of like the same thing. You would take 250 multiplied by 5, because that's the amount of contributions that you made. It's 5 times 250 minus the answer, so second answer, and then you hit enter. Why is it? Oh, sorry, it's the other way around, yeah. But in either case, yeah, this is a low yield, $77.28. Okay, so $77.28 was the earned interest. Now consider this, that over time, if you extended it, you'd make more. If you increase the payment size, you make more also. Now, pay attention to how I will demonstrate an annuity using the calculator, specifically the TI-8384. Go to Apps, Finance, TVM Solver. Now, in this case, how many times was I making a deposit? I was making it like 5 years annually, so 5. The percentage rate was very low. It was 3, so 3%. It's not a present value, but it's minus 250. So minus 250. The future value is unknown, so let me just put a 0 there. But the period, what was it? It was 1. Okay, but we need to go back to future value. We clear it, because if I move, I save it as last, because if I move, I can't do anything. So push alpha, enter, and what do you know? There's the answer. 13.2728 cents. Okay. So it would be nice if you can go back and use the exact same formula, or the exact same app on the calculator to use this. But of course, you might need to show what formula did you use. So just keep that in mind as it relates to what formula are you going to use. Now, the remainder of this video may just look at just a few examples of functions and such. Now, you can use the formulas, by the way, for these problems. Now, I'll just do a few examples. So, like, let's say that we're dealing with a quadratic function. And let's say that you have y equals to negative 2x squared minus 16x minus 30. Let's say that you wanted to essentially graph this equation, or maybe even find the vertex, find the x-intercepts. You would have to complete the square. So to do that, you take out the negative 2, and you have x squared plus 8x. You take half of 8, which is 4, and you square it, which is 16. But you have minus 32, not minus 32, but minus 30, and then you have plus 32. So in this case, you have that this is going to be negative 2 times x plus 4 to the second power, and that's going to be plus 2. Now, in order to find basically the graph of the equation, we now know that the vertex is actually negative 4 comma 2. And then from there, we just need to find the x-intercepts. How do you find the x-intercepts? You set the equation to 0. So that would give you 2 times x plus 4 to the second power equals to 2. And then that would give you that basically x equals to negative 3 comma negative 5. Okay, so these are the x-intercepts. And if you're wondering, like, how did I do that, then make sure that you divided by 2 first, and that you took the square root afterwards, and that you accounted for the plus and minus 1. And then from there, that's where you get the minus 3 and minus 5. But my whole thing about this is that once you complete the square, then basically everything kind of falls through. So let's actually just use Desmos, because it'll be a lot quicker for me to just graph it there, and then you can see what it looks like. So y equals negative 2x squared minus 16x minus 30, and let's go home. Okay, so there's the vertex, there's the x-intercept, there's the x-intercept. Where's the y-intercept? It's minus 30, right? So just go down, and there's minus 30. Okay, so we have that's going to be the graph of that equation. Now, similarly, if you were going to graph any other parabola, then you can do the exact same thing, especially if it's not a perfect square. I'm sorry, not a perfect square, but the asymptotes are not like whole numbers, for example. They're irrational, so to speak. Oops. Now, you also talked about rational functions, and really the only thing that we need to know about rational functions for the most part is their asymptotes. So, like, for example, if I have a function like y equals to x squared minus 4 divided by maybe like x squared plus 5x plus 6. Well, I would have to first of all factor this as x minus 2 and x plus 2 divided by x plus 2 and x plus 3. But what ends up happening is that you end up with x plus 2 cancels out, which basically means that the equation is now written as x minus 2 and x plus 3, with the additional condition that x cannot equal to negative 2 because it has a hole. Okay, so there's a hole at x equals negative 2. But what does that mean also? That there's a vertical asymptote. There's a vertical asymptote at x equals to negative 3. So in any case, like, we can, graph this in the x and y plane if we wanted to. Now, if we do, then in that case, all that you need to do is just draw 2 asymptotes, the vertical and the horizontal. I might have forgot the horizontal, actually. The horizontal's at 1. How did I know that? It's because you look at the degree. If it's the same, then basically it's the ratio, so it's y equals 1. Now, in terms of finding the value, you can use the x-intercept. I mean, the x-intercept is at 2. So, and then if you plug in 0, you get minus 2/3. So I think that the graph is probably something like this. It's not a good sketch, but we can look at it in a second. So this is a rough sketch of the graph, but let me go ahead and just plug it in here. And we're going to plug it in as it was written initially, where you had x squared minus 4 divided by, how was it, it was x squared plus 5x plus 6. Okay, and then go home. Okay, there's much better graph. So notice the asymptote right here. But notice that it was undefined at -2. And let me see, -2. Oh, wait, -2 is over here. Sorry. And there's where it passes through the x-axis. But where's -2? It's right there. It's undefined, see? You have that little hole right there. Okay. So hopefully that kind of helps in terms of what are you supposed to get out of the graph, essentially. You're supposed to be able to sketch it and use the asymptotes or look at the asymptotes. Now, if you want let's say another example. Another example could be very similar to the previous one, where if you have, for example, y equals to x minus 2, or how about x plus 2, divided by x minus 2, it becomes clear that the vertical asymptote is just x equals to 2. The horizontal asymptote similarly is equal to 1. Why? Because it's the ratio. So it's 1. But the x-intercept is at -2, 0. Okay. Where's the y-intercept? It's at 0, -1. Now, what do we need to do as it relates to this graph? Well, we need to go ahead and just find the asymptotes respectively. So you'd have y equals to 1 right there. And then you have a vertical asymptote at x equals to 2. So this could be x equals to 2. But notice that you have points that cross at -2. And you have at -1. Okay, so this graph, similarly, it's going to look terrible in terms of how I try to graph these. Okay, I wonder if I can fix this. Okay, not so much of an improvement, but it'll do. So this would be our equation in either case. Now, let's look at it in the x and y plane though. So y equals to x minus 2. All of this is, let me just do this, x minus 2. Was it plus 2? Yeah, it was plus 2. X minus 2. There we go. So this is a much better graph. But notice that we can plug in y equals to 1, and we'll see that it never touches that graph. But to be more specific, if we were going to draw it, we should do we should do that. And then if you go ahead and you use x equals to 2, and then maybe we can draw that too. Use a green line, and then there. Okay, so we see that this is our graph of our equation. Now, consider this though. If we look at transformations, then we can probably then just say, well, isn't this just the same graph as 1 over x? And it's just shifted a couple units up and down, or maybe to the right and up by 1 unit. And you would find that is completely true, essentially. It just depends on how much was it scaled by, for example. But I can create like an example just so that you would see a over x minus b, and then plus c. Oh, plus c. And let me deactivate this for a little bit. Okay, so if I go ahead and I make it equal to 1, that's the original factor. But if I go ahead and I move it to 0, and then I move this down a little to 0, can I move the graph to the left and right? The answer is yes. And then can I move the graph up and down? The answer is yes. But can I scale it? And the answer is yes. So see like how that moved it away. But if I do the opposite, what is it doing? It's making them closer. But of course it can't reach these values won't ever touch actually. Okay. So this is an example of how we can scale the equation by doing these transformations. That's kind of neat actually, though, when you think about it, especially because of the fact that if you take pre-calculus, you'll realize that that's actually a hyperbola just rotated a few degrees, basically. But yeah, I mentioned that all you need to know is asymptotes, actually. Now, I'll try to conclude this by looking at some exponential functions. So we look at some exponential functions, such as like you have 4 to the x equals to 16. And we can technically solve these kinds of equations because we can rewrite 16 as 4 to the 2 equals to 4 to the x. And then that gives us that x equals to 2. Okay, that was easy. Now, the thing though is that what happens when it's a little more complicated, right? So like if you have 9 to the x plus 3, and that's equal to 81 to the 2x minus 5, well, 81 is 9 squared. So that's 9 to the 4x minus 10. Now in this case, this would mean that the exponents have to be equal, right? Okay, well not this one, but this one. So 4x minus 10 equals to x plus 3, and that will be 3x equals to 13, and x equals to 13 thirds. So the answer is 13 thirds. Okay, now, if I wanted to though, I could probably solve that equation by using a logarithm, for example. But, maybe you don't want to use logarithms because maybe you didn't get to look at them. But, like if we do, like if you have a to the x equals to y, you can technically rewrite this in terms of the base and what it is. So like you'll say like a log base a of y is equal to x. And basically that gives you that x equals to log base a of y. Now, in any case, though, you have that these types of equations can be rewritten using base 10 or base e, meaning that you could rewrite it as ln of y divided by ln of a, or using base 10, you have that it's log y divided by log a. Okay, but how do we use that to be precise? Well, let's say that you had 5 to the third equals to 125. You can rewrite this in terms of a log, where you say log base 5 of 125 is equal to 3. So that would say log base 5 of 125 equals to 3. The only thing, though, is that we already have the answer technically, right? But suppose that you had a different equation, like 2 to the x equals to 3. There's no way that we can find the exponent that matches this one. So in that case, that means that the only way to do this would be to say log base 2 of 3 is x. So that would be log base 2 of 3 equals to x. But how do you solve the equation? You rewrite it as ln of 3 over ln of 2. What's the answer? Okay, let's see. $1.585. So 1.585 is the answer. Now, consider this, that it does make sense because 2 to the 1 is 2, and 2 squared is 4, and 3 is somewhere between there. So in that case, I knew that the answer was somewhere between, for x, that it was somewhere between 1 and 2, basically. Of course, we could solve this using Desmos, though, too, where we just say, okay, we'll just plug this into your calculator. Maybe we can just make a new graph. Yeah, let's just make a new graph. Y equals 2 to the x, and y equals to 3. Point and click, done, 1.585. Of course, if you're having to show your work, then that doesn't really work. So let's see, what else do we... Yeah, so you can practice going from one to the other. If you have log base 6 of 36 is equal to x, then you know that means 6 to the x equals to 36, which is 6 to the x equals to 36. But, you can figure that out, that's going to be just 2. But what if you had different equations? What if you had an equation such as log base 4 of, let's say, 3x minus 2, and that's equal to the 1. Okay, now, in this case, this is telling you that 3x minus 2 has to equal to 4 to the 1. Okay, so in this case, that would mean that by solving for x, you get 3x equals to 6, and that tells you that that x equals to 2. Okay, so x equals to 2 for this problem, okay? Now, similarly, though, if you had an equation, let's say you had an equation like log base 4 of x minus 4 plus log base 4 of x plus 8 is equal to 3, then this is actually kind of like the same thing, but the only difference is that you need to multiply. So you have that log base 4 of x minus 4 times x plus 8 is equal to 3. Okay, so that'll be x minus 4 multiplied by x plus 8 equals to 4 cubed. And let's see, okay, this is going to be x squared plus 4x minus 32 equals to 64. Okay, so that's going to be minus 96, so x squared plus 4x minus 96 equals to 0. Now, to solve that equation, basically that's going to be x plus 8 times x minus 12. Actually, it's, no, sorry. It's x minus, x minus 8 times x plus 12 equals to 0. But when you solve this, you get 8 and negative 12. However, the one that doesn't work if you check your work, check your answer, is minus 12 because it's extraneous. So the solution actually is just 8. And you can verify that actually. Now, I don't think that there's anything else that I can really talk about in either case as it relates to logarithmic equations. Let me see if I can do another example. There might be another one. Yeah, we can do this one. So let's say that you have an equation e to the x minus 1 equals to 8. Okay, so this could be log base e of 8 equals to x minus 1. But log e is ln of 8 equals to x minus 1. But that means that basically x equals to ln of 8 plus 1. Okay, so what's our answer going to be? Okay, so ln of 8 plus 1, and that's 3.0794. Okay, so we have that this is going to be our solution for, solving that equation. Now, of course, if we wanted to, we could look at, another type of equation, like if we had, maybe like e to the x squared minus 6x, and this was equal to maybe like e to the 8, then essentially this would be the exact same thing where you would say that the exponents must be equal, because here you have that the bases are the same. So x squared minus 6x minus 8 equals to 0. And then you would just solve this equation as needed. But check this out. This might not have like a whole number. So let's say x minus 6 plus 9, and then we have minus 8 plus 9 equals to 0, right? Now, from here, we would say that you'd end up with x minus 3 squared equals to negative 1. And basically, once you get to there, there's no solution, actually. Because if you take the square root, you end up with a imaginary unit in either case. Now, as it relates to kind of like some applications I encourage that you do look at the applications that relate to exponential and logarithmic equations on your review, that is, and also your big assignment, unless you're using the season episodes assignments, then in that case, you probably went through it in section 10.6. So go ahead and just look at 10.6 and be sure that you know how to solve things like that, whether it's exponential growth or exponential decay. Okay. So in either case, like, make sure that you do have a calculator that has the scientific capabilities. You will be required to show some work for some of your questions, and others you may not actually, but it is going to be very similar to the exam 1 review in either case. I hope this helps, and let me know if you have any questions.